Yeah, early stopping, I think I told you data set augmentation, I said L2 norm on the weights is where we started, right? So this regularization, as we move forward. So one of the other ways to actually regularize is to introduce a regularizing term. And regularize means various things. For example, restoration problems and all. The classical way of calling what regularization is a little sort of this one different. Here by regularization, as I said, what we really mean is that, that we would like. I mean, what do you say, right? I mean, we'd like to kind of reduce the weights, right, which we're using, the total number of weights. We want to kind of make sure that only those weights play a role, right, that really have to play a role. And one way to do that is to is to actually introduce an L2 norm on the weights, and which then leads to a modified sort of a cost function. So then, like I said, I think last time I written some L tilde theta for that, right? So if you go to that expression, so what we had was, yeah, L tilde. Okay, if you just talk about weights, I'll write it as omega. Okay, so to be more kind of specific, if you're talking about the weights, L omega plus, let's say, some beta by 2 norm of omega square, norm of W square. So this L omega is still the same old cost, which could be a mean square error or which could be a cross entropy loss, right? So this can be an MSE or a cross entropy depending upon what kind of a problem you're solving. By the way, right, so this cross entropy, right, talking about this cross entropy, there is something that you should be aware of, which I will just, this will be a brief sort of a digression, but then we'll kind of quickly come back. There's something called a softmax, which is used when you talk about a cross entropy. Okay, this is like a module that they actually put, I mean, so right now what you have is, let's say if you're doing a classification problem, right, you will come till the end, till the output layer. And in the output layer, right, I mean, you can actually think about, because you have, let's say, right, I mean, you have a network, right, which takes some input, and then let's say, right, you've got, let's say the simplest case is what I mean, you can think about, right, two, so you can think about just to see two outputs, okay, in the simplest of cases. Let's say I'm just trying to do a 2-class problem. I want to say whether it's a foreground or a background, right? So then what you can, then in such a case, right, you will have maybe a success for, let's say, a foreground is P, then a success for the background is 1 minus P, right? And this layer, right, which you have at the output, that is actually sending you that value. I mean, you can think of, because you need a probability as the output, because you're trying to solve a classification problem, you might want to say that I would rather use a sigmoid there, because I know that a sigmoid will go from 0 to 1. Therefore, right, I would just want to use a sigmoid as my activation function at the output, so that the values, right, are actually, they would be a probability. They'll sum to 1, between 0 and 1, all that, right? But what can happen is, if you kind of, so right, this will be a binomial case. But if you had, a multinomial case where, let's say, you've got several classes, right? I mean, typically one doesn't limit oneself to just a foreground or a background. For example, that ImageNet kind of a classification problem, right, we had 1000 classes, right? So then I mean, it no longer makes sense to talk about P and 1 minus P and so on, right? All that we know is they should all sum to 1. So so it is in such a situation that the softmax comes in, and the softmax actually, right, enables you to not just limit yourself to a sigmoid. I mean, you can have any activation, in fact, at the output, okay, even if it is a classification problem. Because for the earlier case, it looks like you should have a sigmoid, because that is what will output a value between 0 and 1. But that's not actually necessary, especially when you go to a multinomial case, right? When you want to see a multinomial case, then what is done is, so for example, right, you have your outputs coming in from the activation or the output. Then let us say that that those are, okay, I mean, what we'll be using, some y hat, right? So let's say what you're using is some y1 hat. Last time I think that toy example that we took, we had y1 hat and y2 hat. But let's say we have more of them, y2 hat. And let's say we have all the way up to some, whatever, let's say yn hat. So we have got n classes, right? It's a multi-class problem now. And now what we can do is, now because of the fact that, you see, these y1 hats could be limited to values between 0 and 1, or they could even come from some linear activation function, right? We do not know, it could be anything for that matter. Then what is done is, so for example, right, so you would convert this y1 hat into, let's say, let's call this sigmoid, let me just call it as some sigma. Then what I will do is I will take sigma of y1, let's say, okay, in fact for any yi, right, yi hat, I will write this as e raised to yi hat by summation e raised to yj hat, j going from 1 to n, okay, for the n number of classes. So, the thing is that what you do is you actually take the outputs that you get for in fact all the classes y1 hat, y2 hat, and then you sum them up, right, at the bottom denominator, and then numerator you raise e to the, I mean you raise you keep it as e raised to y1 yi hat. Now, the idea is that if you now, one thing is, right, now yi hat, whether it is negative or positive, it does not really matter, it could carry any value. Finally, sigma yi hat will now be a number between 0 and 1, because if you sum up, if I do summation sigma yi hat over all the i's equal to 1 to n, right, that will be equal to 1, because this if you keep adding, right, so it will be the same as whatever is, right, that you can see. So, then it will be like summation e yi hat, and then at the bottom you have summation what is it, yj hat, and they both are equal, and therefore, these values will sum to 1. And it's a kind of a clean way to sort of go from a binomial case where you would have had a situation like p and 1 minus p, and most likely you will think of having a sigmoid there. But a multinomial case, you can directly go using this softmax. So, I think of the softmax as an additional module that is coming in. So, you are still free to do whatever you want prior to that, whatever activation you want to use. Don't limit yourself to 0 to 1 or anything. That can, so those yi hats can be, right, so they can come from a real number. Okay, so they can be whatever they are. There is no constraint that they have to be positive and all. And then eventually, right, you then kind of convert them to a probability. And then what happens is, right, so when you do this cross entropy loss, right, I mean we saw, right, we had like yi log yi hat, right, that is what we had, summation I going from the number of classes, that would be your cross entropy loss. So, this yi, which is actually the true label, right, see, you have a network, and let us say, right, I pass the example of, let us say, a horse image, right, inside. Now, my output vector, right, the sort of a target vector, that would be what, suppose suppose this entry is for horse, which I will have to keep it as fixed, right, through all my experiments. So, what I will do, I will make this as 1 and then kind of, right, reduce all the others to 0, because I will say that this is actually a horse, and therefore, that particular element, so, right, this is going to be your y, okay, and y at some, let us say, kth entry will have a 1, okay, and therefore, right, when you do a cross entropy loss, right, we will do like this, right. So, what you will do is you will have like yi a log, right, I mean yi hat, right, summation over I. So, now what will happen is, so such a vector, so this is a target, this is what you want ideally to be, that is when you pass a horse, you want your y hat to look like this, you should have zeros everywhere except that in that one place, whatever kth position, it should be 1, and then rest it may not happen, right, it will try to get there. So, when you compute the sigma yi hat, you may end up with a y hat, right. So, this is a target. So, this is a target, and what is being estimated is some y hat, right, which is this y1 hat, y2 hat, and so on, and this need not exactly look like y, but then it will try to get there, because that is what we talked about earlier, right, for cross entropy. So you want this yi hat to come as close as possible to yi, right, and such a vector is called actually a one hot vector. Okay, so a vector of this type is called a one hot vector. What it means is that only one element is really active, right, rest of all are all zeros, right. So, it is called a one hot vector. So, if you encounter one hot, okay, don't, so you should know that what is being meant, right, and therefore, so I just wanted to mention that talking about these losses for L of W, right, when you are talking about the loss function for the weight, which is typically the original cost, right, that we have been talking about till now. It could be MSE, it could be cross entropy, whatever it is. But if it is cross entropy, then very likely that you are dealing with a classification problem or whatever, a segmentation problem, where you have got multiple classes, and right, you could be labeling every pixel, or you could be labeling an entire image as whatever, to which class that particular object in that image belongs. So, in that case, remember that there will be a softmax, right, at the after the output layer, and then you convert everything to a probability. Okay. Now, see this. I am just going to indicate an outline, okay, as to how it goes around. So the idea is that, right, by introducing this additional norm on the weight, right. So what you are actually effectively doing is, so suppose I look at the gradient of L tilde omega, because, right, that's what I will have to now use, right. Till now in my iterations I was using dou L by dou W. Now I will have to use dou L tilde by dou W, because that's my new cost. So if you look at this, right, this is going to be gradient of LW with respect to W plus, last time it will be, sorry, this is going to be beta W, everything is a vector here. Okay. So now the argument, right, if you start deriving, right, it's going to take time, but it's a little tricky, but not so tricky. So what you have to do is, you have to do, suppose, let's say, see what you want to understand is, with respect to this new cost function, okay, with respect to this new cost function, if there is an optimum that, let's say, what is the symbol that I am using for that, tilde, W tilde, okay, if that is what is the actual optimum that you get by actually minimizing L tilde omega, and if by actually minimizing the delta L omega, the L omega, if you had L omega as your cost, just L omega as your cost, and suppose you had omega star as the optimum for that, okay, then you want to see how is omega tilde or W tilde related to right, W star, right. That is the idea, because something will change because of this additional factor which will get involved when you use this new cost, right. Now the way right, this is arrived at is, I will write the final expression, but the approach is that you expand this guy in terms of a Taylor series, right, in terms of a Taylor series, which then means that, right, so what you are sort of looking at, let's say, suppose I call this is U, okay, as a difference, right. So let's say this is W minus, you see, right, W star, where right, W star is this optimum. Then what you can do is, you can actually look at the Taylor series expansion of this guy, W star plus U, okay, and then if you try to right, expand this, then right, what you will get is, L of W star plus whatever, right, U transpose gradient of L, right, with respect to this one, right, W star. So let's just write this as a gradient, okay, gradient L, and then plus you will have a half, right, you will have U transpose, and then H, which is the Hessian of L. This we have seen before, right. I mean, so this is the Hessian of L, and then you will have U, right, something like this is what you will have. And and then because you know that at omega star, right, this guy is 0, right, because, right, that is supposed to be the optimum, right. We have assumed that, say, W star is the optimum for say L omega, right, when you are actually minimizing L omega. Therefore the second term drops out, and then right, what one can sort of look at is really examine this H. So the whole thing boils down to examining H, and you can show that H is actually a positive semi-definite matrix. Why? Because of the fact that, right, I mean, see, if this quantity is 0, right, and if you are already at actually L omega star, which is the minimum, unless U transpose HU is actually greater than or equal to 0, right, otherwise what will mean is you are not really at, you are not at a local minimum, right. You see that, right? See that argument that, H has to be PSD, because if H is not a PSD, then it means that L omega star is not really a local minimum, right. So you have to use arguments like that in order to be able to arrive at the fact that H is actually a PSD, right, under these assumptions. And you can just, right, walk through this a little bit. If you walk through this, I just leave it to you as an exercise, right, just show that, okay, and then what you have to do is, use, do an eigenvalue eigenvector decomposition on H, because now it's a PSD. So if you do an eigenvalue eigen decomposition on H, then that can be like, Q diagonal Q transpose, right, we don't want to use Hermitian and all, so just say, right, Q diagonal, Q transpose, and based upon this, right, and where this contains the eigenvalues of H, right, this is a diagonal matrix containing the eigenvalues of H. So this eigenvalue eigenvector decomposition you are all familiar with, right. So if you use this argument, then what you can effectively show, just 3-4 steps down, and you can actually show that your W tilde, okay, can then be shown as Q diagonal plus alpha, no, beta, okay, we have used beta. So beta I is an identity matrix, inverse, and then diagonal Q transpose W star. Okay, this is what you will get. That means the new weight W tilde, by introducing the additional regularizing term, which is norm of W, right, the L2 norm of W, by introducing that, effectively what will happen is, you will see W tilde your W star will change to W tilde. So you can easily think, right? I mean, if I had forced my beta to be 0, then of course diagonal inverse diagonal is identity, QQ transpose is identity, and therefore you'll be back to say W star. But given that beta is not 0, right? So what will happen is you will have a term like this, right? And therefore, right, if you try to examine entry wise, so what this, so the scaling is actually happening here. Okay, the actual scaling is happening here. I mean, so not just this, so this diagonal also. So what is happening is, right, Q transpose is acting. So Q transpose is a matrix that's actually rotating omega star, and then after that there is a scaling going on, and then after that there is a re-rotation through Q. So the actual scaling of weights is happening in that middle term, right, which is this diagonal plus beta I inverse diagonal. So if you try to examine any one, so in that sense, right, if you want to examine some ith entry, right, then that is going to look like, let's say, lambda I by lambda I plus beta. Okay, that's the kind of scaling, right, which is being applied. And these lambda i's are but the eigenvalues of H. Okay, so what this means is, and generally, right, you know that eigenvalues actually, right, represent kind of variance, right, in the sense that if there is a high spread, right, then you will have, then along that orientation which the eigenvector kind of represents, the eigenvalue sort of says that how large is that variance. You guys are familiar with this, right? When you do a PCA or something, right, what do? I mean, right, you take a covariance matrix, you get the eigenvectors. Then when you want to get a principal eigenvectors, what do? You go and look at the most significant eigenvalues, because orientations you can have in various ways, but then which ones have the highest spread? You start from the sigma that, or the singular value or the eigenvalue, whichever is the highest, then you kind of order them down, right? Because you are sort of thinking that that you have a distribution that is most spread out in let's say one particular direction, then next most spread out is in the other direction, and so on, right? So in the same way, so these lambda i's are kind of, right, so these lambda i's sort of are signifying this importance, and what this means is that if lambda I is actually pretty high, then you see beta, and of course beta is actually a positive number, so it can be greater than, it can be equal to 0 if you don't want the regularizing term. But when you are talking about regularization, of course, it's a number greater than 0, then what you see is that, right, so you see that the scaling rate is almost equal to 1 for that particular weight, which means that it's a fairly significant sort of weight, and then you don't want to sort of knock it off. Whereas if you have a situation, right, where so the other situation is when you have lambda i's, right, like much less than you see beta, right, I mean, in which case this will almost go down to 0, because I mean you have a beta, right, which is much greater than lambda I, so this denominator is almost like beta, and lambda I by beta can go close to 0. That means where the spread is really not much, in which case that weight is probably not even significant, and you want to sort of, you may not reduce it to 0, but you're sort of, right, you're sort of alleviating its importance, right? So you sort of, right, bring it down. So in a sense, this happens automatically, right? And the only control parameter, sort of a hyperparameters, is beta. So such things are called hyperparameters. Okay. So you had unknown parameters that you are anyway estimating. So those are learnable, right? Within a network, always, right, keep in mind that there are things that are learnable, like the weights, the biases, and so on, and there are things like these hyperparameters and all, which you don't call them as trainable or learnable. So these have to be figured out. So you have to kind of tinker with it. So for a particular problem, a certain beta might work well, and for another problem, the same beta may not work. Therefore, these have to be arrived at by actually doing some, brute force experiments. Okay, there's no easy way how to tell what will be a good value for, let's say, beta. Okay, so this beta is called a hyperparameter. And these hyperparameters you will encounter often. In fact, many things are hyperparameters. Even the number of layers that you use in actually a neural network, that's a hyperparameter. Nobody knows how many layers you need to use, and then what should be the right dimension. All these are hyperparameters. Okay, so beta is a hyperparameter. And what you can also show is that right, I mean, effectively, if I do the summation over all the weights, right, I mean, let's say 1 to n, lambda I plus beta, then this number, right, is much less than actual n. So in effect, right, it's like saying that instead of dealing with a value like n, right, you can now deal with something much less than that. But again, right, the beta will work best depends upon the problem. So you'll have to look at your final accuracy, and then sort of right, because you can't arbitrarily make this beta very high, because if you make beta very high, then the actual original cost, right, will lose its importance, right? So you can't just arbitrarily make L2 norm to be of the weight to be the most important thing. So, you have to strike a right balance, and that right balance comes out of this one, okay, experimentation. Okay. So this is about regularization by imposing a regularizing term on the weights. You can also there is an interesting thing, right, which you can do, which is not very obvious. Another way to actually regularize is through noise injection. Is through noise injection. Okay, this is also again one more way to actually to bring in regularization, which again means that something like this kind of well, you can actually show that this is I mean like this. Okay, let's just show this. So for example, right, so what this means is that so okay, so you have, so suppose let's say, right, I have an output, suppose y, right, which is, I mean, right, at some layer, right, I am writing. So this, let's say summation, let's say, right, I am at the final output layer or something, and then I have like summation wi, okay, I mean at some layer, okay, xi plus, now right, what I would normally have had is wi xi, but now, right, I am going to add noise to my input. So this noise injection is to the input. Okay, if I actually inject noise, so this is EI, okay, by the way, and EI is, let's say, Gaussian with 0 mean and right, sigma variance. Okay, let's call this as y noisy. So this y original, right, would have been just the summation wi xi, right, is what I would have done. But the fact that I am injecting noise into xi means that effectively what I will then see is not the original y, but then a y noisy. And this y noisy, right, you can just expand it, so that will become this all over I, okay, and I will be like the right number of terms that you have, and this will be like summation wi xi plus wi ei, and wi xi we know is y, therefore y noisy is y plus, let's say, summation over I wi ei, and I have a target, right, let's say, and of course this noise injection, this is only for an MSE loss, okay, this regularization is for MSE loss, okay. So okay, acts as a regularizer, I mean injection of noise into the input acts as a regularizer provided the loss is MSE, okay, acts as a regularizer for MSE loss. Noise injection, okay, I mean I think I should write this here, noise acts as a regularizer for MSE loss. Okay, now if my final sort of target value is t, and if my target value is t, right, I mean that's what I actually want, then what you can kind of look at is the expectation of y noisy minus t square. Right, I mean, if you right, so instead of y minus t the whole square, now what you have is really y noisy minus t the whole square. It is what you have. So then we can just substitute for y noisy, right, into this. That will be like y plus summation wi ei minus t the whole square, and then this will be like expectation. I can just rearrange this, put this as y minus t plus summation wi ei square, right, and this we can write as, and if, okay, let us just assume that y and t are both deterministic. I mean, if not, then of course you will have to use an expectation there also, okay, nothing great will change, but let us say, just to make matters simple, if you assume that y and t are both right deterministic, then this will become simply y minus t the whole square. If it is not, then you will replace it with the expectation y minus t the whole square, and then this, if you expand, right, so because you are assuming that ei is 0 mean, therefore that product term goes away, and because you are also assuming them to be uncorrelated, right, therefore what will happen is you will have the summation wi square, okay, and then expectation ei square. Or in other words, we can simply write this as sigma square, right, which is the variance, right, this is over I. So now if you kind of look at this term, right, this is like norm on the weight, right? And of course, it's being scaled by this noise variance. If you make sigma to be 1, then it will be like summation wi square, which is exactly what you had earlier, right? You had this right, L2 norm on say w, right? So what this is effectively saying is that another way to regularize, that means, right, you want to sort of bring in an action or bring in a regularization term on the weight, that is by actually adding noise to the input, and that you can, and for an MSC loss, if you can effectively show that this is equivalent to doing a regularization, L2 regularization on the weight. Okay, so all these are tricks that, let's say, right, people play. It's not like, right, everything is done, but depending on problem to problem, right, people try various things, but these are all things that one can try.